Welcome. We have been discussing thermal radiation, and let me briefly recapitulate right at the start what we had discussed in the last class. Thermal radiation is radiation that is emitted by material which is in thermal equilibrium. And if we have radiation that is enclosed in a cavity like this, and the whole enclosure and the radiation inside comes to thermal equilibrium at a temperature T, then the radiation that is inside this cavity is referred to as black body radiation. And we had seen in the last class that this radiation, the spectrum of this radiation, the specific intensity, is just a function of temperature, and this function is called the Planck function. We had also seen that if we have some material which is at a temperature T, the material itself is in equilibrium, then the source function for this material which is in thermal equilibrium is the Planck function. So, these are two different things. So, this is called a thermal radiation that originates from such a material is called thermal equilibrium, is called thermal radiation. It need not be, the radiation itself need not be in equilibrium with the material. So, the specific intensity of the radiation could in principle be anything. If the specific intensity of if the radiation comes to equilibrium with the material, then the specific intensity becomes the Planck function, otherwise just the source function is the Planck function. This is called thermal radiation, this is called black body radiation. Okay. Then having discussed this, we went ahead and we calculated the entropy, how the entropy on this depends on the temperature and the volume, and based on this we finally reached the conclusion that the energy density of this black body radiation is proportional to T to the power 4, and this constant of proportionality we called it AB, the Stephan constant. Further, we also saw that the Planck function, this we had seen earlier, that the specific intensity is related to this. You multiplied by C and divide by 4 pi, you get the specific intensity. So, the Planck function, the total if you integrate this over frequency, the Planck function over frequency, then that is equal to C into the energy density by 4 pi. The flux, the brightness, this is the brightness, is C into the energy density by 4 pi, which also scales as T to the power 4. And the flux from any surface of a black body cavity we saw is also scaled as T to the power 4, and this constant is called the Stephan-Boltzmann constant sigma, and it is related to this Stephan constant like this. So, it is C into the Stephan constant by 4. We also calculated the entropy, and the entropy we saw is proportional to T cube 1 power of T less, and it is equal to 4/3 into the energy density by the temperature into the volume of the system. So, the entropy density is 4/3 energy density by T. After that I told you that, okay, that we also looked at what happens when you have adiabatic expansion of radiation, and we saw that for radiation which is made to expand or contract adiabatically, PV to the power 4/3 is a constant. So, radiation behaves like an adiabatic medium with adiabatic index 4/3. Okay. Having done all of this, I told you that from my macroscopic thermodynamic considerations you cannot proceed much further. To determine these constants, the Stephan constant or the Stephan-Boltzmann constant, you need to look at the microscopic nature of this. So, we looked at, that is what we were looking at, and in the last class, at the end of the last class, this is where we had reached. So, we had calculated a relation between the specific intensity. Remember, the specific intensity I knew is for rays in a certain direction. So, this is a unit vector along the direction of the rays. Let me draw a picture. So, these are my rays that okay. So, they are along some unit vector n and they will be in a spread of solid angles. So, the specific intensity at a frequency nu in this particular direction of the unit vector n is related to the occupation number of the photons. This n over here is the photon occupation number, and photon occupation number of a particular mode, the mode being the vector wave vector k. How is this mode related to this frequency and the direction in which the wave is propagating, the ray is propagating? The wave vector k. So, the direction of this, it is obvious, is going to be same as the unit vector n. That is the direction in which the right ray is propagating, and the magnitude is going to be 2 pi omega, and omega we know is, so omega is equal to c into k, right. So, we can write this as 2 pi c into k. So, omega 2 pi omega, and omega is c into so we can, yeah, so this is going to be right omega. So, this is the modulus of k. The modulus of k is omega by c, and omega is 2 pi nu. So, we can write this as 2 pi nu by c, right. That is the modulus of k, the magnitude, into the direction of the vector. So, we have a relation relating the specific intensity in this direction to the occupation number of a mode k with these factors outside. These factors, one of them comes from the energy of the photons and others come from just counting considerations. H nu comes from the energy of the photon, and others come from just counting considerations, and factor 2 comes here because light has two polarizations and we are assuming that the light is unpolarized. So, both are equally present. Okay. So, this is a very important relation. It has got several applications and we shall see these as we go along this course. Right now, it is a very general relation between the specific intensity and the occupation number of the modes of the photon. Okay. Right now, we are interested in a situation where the photons in this cavity are in thermal equilibrium with the walls of the cavity. So, they are in thermal equilibrium at a temperature T. Now, photons we know follow there are two statistics, fundamental statistics. One is the Bose statistics, the other is the Fermi statistics. Now, photons are, what are photons? They have spin 1. So, they are bosons, right. So, photons follow the Bose statistics. So, the occupation number n, so if the photons are in thermal equilibrium, that is what we are assuming, right. If they are not in thermal equilibrium, the occupation number could be anything. But if they are in thermal equilibrium, then the occupation number is given by the Bose statistics. And there are two parameters here. One is the temperature of the system and the other is the chemical potential mu, which, so there is a system which is of bosons in equilibrium. So, to completely specify the system, you need to tell the temperature and the chemical potential, right. The Bose distribution has two unknown parameters, the temperature and the chemical distribution, chemical potential. Now, photons are not conserved. That is something I should have mentioned right in the beginning also. So, you can use these thermodynamic considerations to calculate the energy and then everything else, because photons can be destroyed and created. Okay. So, the number of photons essentially adjusts itself to the temperature. Depending on the temperature, the number of photons will go up or down. Okay. So, for things, for particles, bosons that are not conserved, whose number is not conserved, okay, there is no conserved quantity associated with the photon, there is no charge, there is no mass is not conserved anyway, but there is no charge associated with the photon. So, these are massless uncharged particles. So, the chemical potential, they have no charge whatsoever, no kind of charge. So, the chemical potential is 0, and then you can straight away write down the occupation number. In thermal equilibrium, this is isotropic and it is 1 by, it is a Bose distribution with 0 chemical potential. So, it is 1 by exponential the energy by kT, and the energy we know is h nu by kT, this minus 1, that is the Bose distribution. So, the wave number is converted to frequency. We have just seen how to do that, and you put it in here, and this tells you how many photons there are in this mode. Okay. So, once you assume that it is in thermal equilibrium, it is, you can straight away just plug it in here and you get the Planck function. Okay. So, just plug it in here. If it's in, so these photons are in thermal equilibrium with at temperature T with some material, right. Photons do not interact with each other, so they cannot come to thermal equilibrium by themselves. You require the cavity or some material which will bring it to thermal equilibrium. Once they come to thermal equilibrium, their occupation number is given by this Bose distribution, and we can straight away write down the Planck function, which is 2 h nu cube by c square into the Bose distribution, Bose occupation number. So, we have 2 h here is the Planck constant, okay, bear this in mind, and k, we shall use kb here to distinguish it from the wave number. So, kb is the Boltzmann constant, h is the Planck constant and kb is the Boltzmann constant. So, the Planck function is 2 h nu cube by c square, and here we have 1 by exponential h nu by kT minus 1. Okay, so that is the Planck function, that is the specific intensity of black body radiation. This is kb of black body radiation. Okay. So, let us now look at the behavior of the Planck function, both as a function of frequency and as a function of temperature. So, let us now spend a little time just looking at this. So, the spectrum of black body radiation, how does it depend as a function of frequency at a given temperature, or if you fix the frequency, how does it vary with temperature? Let us look at these. Okay. So, first we will consider a certain limit, the limit being the situation where h nu by kb, the Boltzmann constant, into T is much less than 1. So, this is called the Rayleigh-Jeans limit. Okay. So, we will first study the Planck spectrum in the Rayleigh-Jeans limit. What we mean is that h nu by kb T is much less than 1. So, the temperature of your system defines a frequency, and that frequency is basically kb T by the Planck constant. If the frequency that you are looking at is much more than that, is much smaller than that, Okay. So, the frequency that you are looking at is much smaller than that. Let us see what happens. So, if h nu by k t is much smaller than 1, then we can expand this in a Taylor series, and this will become 1 plus h nu by k t minus 1. So, 1 cancels out. So, the occupation number in this limit n k, let us just look at the occupation number, that also is interesting, is k b t by h nu, which is much greater than 1, because that is the inverse of this. So, each mode is occupied by a large number of photons, that is the limit that we are looking at. Each mode is occupied by a large number of photons, it is very densely populated. Okay. That is the limit that we are looking at, and in this limit the Planck function so this whole factor is now kBt by h nu. So, one factor of h nu cancels out, and what we have is 2 nu square by c square, the Boltzmann constant, into the temperature of the radiation, which can also be written in a form that is quite easy to remember, 2 kBt by lambda square. Okay. So, in the Rayleigh-Jeans limit we see that the Planck function takes a relatively simple form. If at a fixed temperature you look at the specific intensity, then the specific intensity or the amount of energy increases proportional to the square of the frequency, that is the first thing, or it goes down as 1 by lambda square. So, the higher the frequency, the more the energy contained in this radiation. This works as long as you are in this regime, okay, and it is linearly proportional to the temperature. So, if you increase the temperature, make it twice, the energy contained will also just double. Okay. And the other interesting feature to note is that the Planck constant does not appear anywhere over here. It is purely classical in that you do not need any quantum mechanics to understand this, okay, which is again can be understood intuitively from the fact that you have many photons in each mode. So, the photon nature, the discrete nature, does not manifest itself. You have a large number of photons in each mode, and you can think of the electromagnetic wave as actually a wave. The photon nature does not manifest itself, okay. And much of radio astronomy works in this regime, in the Rayleigh-Jeans regime. So, this is very useful if you are doing radio astronomy, for example. Radio astronomers always use this. They do not have to bother about, in most situations they did not bother about the entire Planck spectrum. This is adequate. Now, there is the other limit, that is the Wien limit, or the Wien spectrum, and here it is assumed that h nu by kBt is much greater than 1. So, if h nu by kBt is much greater than 1, the occupation number is essentially exponential minus h nu by kBt, because this number is a very large number, much greater than 1. Okay. So, the occupation number and you see that this is obviously much less than 1. So, the photons in each mode, there are very few photons, much less than 1, okay. This is the average occupation number. So, you expect to find typically less than 1 photon in each mode. Okay, and in this regime the particle nature of the electromagnetic radiation actually starts to manifest itself. It is in this regime. Okay, and in this regime the Planck spectrum now becomes 2h nu cube by c square exponential h nu by kb t minus. So, there is an exponential cutoff. This function falls off rapidly because of this exponential. So, if at a fixed temperature, if you increase the frequency, this function falls off rapidly with temperature. Okay, so let me show you a graph showing these are the two limiting situations. Let me show you a curve. This picture over here shows you the behavior of the Planck function. This shows you the Planck function for different values of the temperature. So, let us just focus on any one of them, okay, for first. So, let us just consider any one of them. Let us consider, say, this one over here. Okay, so this is for 1 Kelvin, 10 Kelvin, 100, 1000, all the way to a million. So, if you look at any one of them, you see at low frequencies, this is a log-log scale. So, both of these are intervals are logarithmically spaced. So, this is proportional to nu square, and then it increases, and then there is a maximum somewhere, and beyond which it falls off exponentially. The exponential cuts it off. Okay. So, that is the first feature that we see of the Planck spectrum. So, at low frequencies it increases as the frequency square, and then there is a maximum somewhere, and then beyond that it falls off. There is a characteristic frequency, and obviously the characteristic frequency is decided by kb into T. It depends on the temperature. The higher the temperature, the larger the characteristic frequency. Okay. So, this is something that okay, before we come to this, let us ask the question, what happens if I fix the temperature? So, if I fix the temperature and look at a fixed frequency, so if I fix nu and look at b nu as a function of T. Okay, so I am at a fixed frequency. Let us say I look at this point over here, which is 10 to the power 10 hertz, and vary the temperature, increase the temperature. Now, it turns out that del B you can do this and check for yourself. It is straightforward. I am not going through the exercise. You just differentiate it with respect to time, the expression that we have, with respect to temperature, and you will find that this is positive. Okay. So, it means that if I increase the temperature, the value of the specific intensity is at a fixed frequency, the value of the specific intensity is going to increase. Okay. So, that is what we have here. So, if I fix the frequency and look at the curves for different temperature, they all lie on top of one another. Okay. So, as the temperature increases, the value of the specific intensity goes up. Okay. So, these curves never intersect, right, because at a higher temperature the curve is always above the one at a lower temperature. So, these curves never intersect. So, if I observe some radiation and I can measure, if I know it is a black body, and if I can measure just any one point on this curve, I know that the temperature immediately, it is unique. Okay. So, if I know that it is a black body spectrum, and if I can measure just one frequency, then the temperature is uniquely determined, because the curves do not intersect. Okay. So, from just one measurement over here, so I measure, if I can determine the entire temperature, provided I have some a priori information, or if I assume that it is a black body radiation. Okay. This is the first thing. Second thing is, you can determine where the maxima occurs. Okay. So, in frequency. So, at a fixed temperature, fixed T, and ask the question del B, where is this 0? This will give you the value of the maxima. Okay. And we see that if you do this exercise, or if you look at the curve over here, so if you look at the curves over here, you will find that nu max by T, this is a constant, okay, and the value of this constant, it is 5.88 into so hertz by Kelvin. Okay. So, this tells us that, which you can determine this again, I am not going through the algebra, but you can determine this, it is quite straightforward an exercise. You have to just differentiate the Planck spectrum with respect to frequency and then set it equal to 0. So, you have to just differentiate this with respect to nu. So, there is nu here and nu here, and then set it equal to 0. If you do this exercise, what you find is that the frequency where you have a maxima scales proportional to the temperature, and the constant is given over here. This is called the Wien displacement law. Okay. Now, here we have been discussing the specific intensity, which is the energy contained in a ray per frequency interval. Now, people also often discuss another quantity, which is the frequency, the energy contained per wavelength interval. Okay. Which is B lambda, the Planck function as a function of lambda. Okay. It is not just the Planck function as a function of lambda. So, B lambda d lambda is equal to B nu T nu. The same energy is contained in the corresponding energy wavelength interval, and we know that so we know that we can write this as the mod of d nu d lambda. So, which essentially tells us that B lambda is equal to B nu, and this, if you differentiate nu by lambda, you will get C by lambda square. Okay, so these are two different quantities. Not only do you write it as a function of lambda, but it also tells you the energy arriving in that interval of wavelength, in a unit wavelength interval, whereas the specific intensity that we have been dealing with tells us the energy per unit frequency interval. Now, these curves, let me just show you a picture of these curves. These curves obviously look different. So, this picture shows you B lambda, okay, effectively. Forget about the scale over here, this shows you the behavior of B lambda. Here again you have a maxima, and as you increase the temperature, the maxima shifts to a smaller wavelength. Okay. So, you can differentiate this also with respect to lambda and set it equal to 0, and you have then you will get a relation that lambda max, that is the wavelength where B lambda is a maximum, into the temperature T, this is equal to 0.29 centimeter Kelvin. Okay. This is also known as the Wien displacement law. So you can use either of them, both of them refer to Wien displacement law, and this tells us where B lambda has a maximum, and the one that we considered earlier tells us where the B nu has a maximum. Now you cannot convert lambda max and lambda, you cannot relate them lambda and nu max by just a factor of C, because they are the maximas of two different functions, okay, they are slightly different. Okay. So the key point here is that as you increase the temperature, the maxima shifts to higher and higher frequencies, whichever you look at, shifts to higher and higher frequencies or smaller and smaller wavelengths. Okay, and just as an example, look at these curves. Then we see that at around 1 Kelvin or 10 Kelvin, somewhere over here, the maxima are all in the radio microwave region. Okay, whereas for few thousand over here, it's in the optical, visual range or ultraviolet, visual, infrared, and if you are looking at 1 million or so, it is in the X-ray. Okay, that's how it keeps as you increase the temperature, the spectrum, the peak of the spectrum shifts, and the bulk of the radiation is also shifting toward higher and higher frequency range. Okay, so that is a brief discussion of the nature, of the shape of the Planck spectrum. Now let us ask a slightly different question: what is the total energy density in the Planck spectrum, right? So our aim was, after all, to calculate that constant AB or sigma from these microscopic considerations. Okay, so let us ask the question: what is the total energy density in the in this black body radiation? And to do this, what are the things that we have to do? So the total energy density, we have seen, you have to take the Planck spectrum. Let me go through this. So you have to take the Planck spectrum, and you have to, so we know that the energy contained in a particular set of rays in a particular direction, this in a particular direction, this is just this quantity into, rather this quantity divided by C, and if you want the total energy density, then you have to also integrate over solid angle, and you have to also integrate over frequency. Okay. So this, the frequency interval we shall do next. Okay, so this gives us the total energy density of the black body radiation of contained in rays in all direction, and this d omega integral can just be taken outside. So this is equal to how much is this? Let me write down. So this is equal to 8 pi, sorry, 4 pi, this will give us 4 pi. So I have 8 pi, I am just multiplying this with 4 pi, and here I have h nu cube by c cube into 1 by exponential h nu by kt minus 1. So this is the energy density at a frequency nu in the black body spectrum, and to calculate the total energy density integrated over all frequencies, I have to integrate this over all frequencies. Okay. To do that, it is convenient to introduce a new variable. Let us call that variable x. such that x is equal to h nu by the Boltzmann constant into T, right, which makes this whole thing dimensionless. So let us do that. So to do that, if you do that, then this integral, this becomes, so the quantity that is integrated is x cube dx e to the power x minus 1, right, that is what is to be integrated, and the rest are just constants outside. So let me write down those constants. I have 8 pi and we shall have kb. So we have to multiply with kb to the power 4 and t to the power 4, right, so that we have, because we have 4 x's over here, we had d 4 nus, nu to the nu cube and d nu over here. So I want to convert them into x. So I will have this factor k, I have to multiply this with kbt h to the power 4. So I have this, and in the denominator I will have c cube, and I will have h to the power of 3. One power of h is cancelled out with this, okay. And this integral, we know this integral has a value pi to the power 4 by 15. Okay, this integral has a value pi to the power 4 by 15. Okay. So now you see the energy density is some constants into t to the power 4, and these constants we had given the name the Stephan constant. So we can straight away identify what the Stephan constant is. The Stephan constant AB is equal to the Stephan constant AB is equal to, let us identify what it is. So I have 8, and I have in the numerator 8 pi to the power 5 kb to the power 4 by 15 c cube and h cube. That is the Stephan constant, and this has a value. Now you put in, all of these are all fundamental constants. This is the Boltzmann constant, this is the Planck constant, this is the speed of light, and pi. So you put in all the values, and what you get is that this is equal to 7.56 into 10 to the power minus 16 joules per meter cube by Kelvin to the power 4. Right. So we have worked out the Stephan constant, and we had seen earlier that the Stephan Boltzmann constant sigma, the Stephan Boltzmann constant is c times c by 4 times the Stephan constant, okay, and this has a value which is equal to 5.67 into 10 to the power minus 8 watts per meter square, that is the flux per Kelvin to the power 4. Okay. So So we have calculated the two constants that we had arrived at just from purely thermodynamic and macroscopic considerations. So this tells us the total energy density in black body radiation. This tells us the flux that is emitted from the surface of a black body. It emits, so for this watts per meter square, Kelvin to the power multiplied by the temperature. Okay, so you will get it in watts per meter square. That is the flux. Okay. So I hope all of this is clear. So this kind of brings to an end our discussion of black body radiation. Okay. Now in astrophysics we we do encounter black body radiation, but the black body radiation also serves as a very useful tool in quantifying as a kind of model which we use to quantify any other radiation. Okay. So there are various kinds of effective temperatures. So it is often convenient. See, we receive the radiation from some source, from some astrophysical source. Now we would like to associate a temperature with that source based on the radiation that we receive. After all, the radiation itself, we would like to use it to infer something about the source. So we use the radiation that we receive to infer certain temperature of the source. Okay, and this is called an effective temperature for the source. The real temperature of the source we do not know, but this gives us some handle on what we call the effective temperature of the source. And these effective temperatures okay, these are related to the black body spectrum. And there are different effective temperatures, so which are used in astrophysics. So let me go through this. So one of them is called the brightness temperature. Now what is the brightness temperature? Let us just see. So we are receiving, suppose we have measured the brightness of the radiation from a source. By brightness we quantify the brightness of the radiation using specific intensity, right. So suppose we have measured the specific intensity of a source of the radiation from a source, and now suppose we assume that the source is a black body. If we assume that, then we can say that if it were a black body, then this should be equal to the Planck function at some temperature T, right. I have measured the specific intensity at some frequency from some source. Okay. So I have measured just one value of nu. I have measured the specific intensity at a particular frequency. If I assume that it is a black body, then that directly tells me the temperature of the black body. This is called, this temperature which I associate with the radiation is called the brightness temperature of that radiation. Okay, it quantifies the brightness of the radiation. And in the Rayleigh-Jeans limit, this is rather simple. So if I take the in the Rayleigh-Jeans limit, which is very useful in radio astronomy, this is quite simple. So in the Rayleigh-Jeans limit, this is going to be, you take the specific intensity and just multiply it with c square and divide by 2 nu square, it will give you the brightness temperature, right. So if it were a Planck spectrum, the temperature would have been this much. In the Rayleigh-Jeans limit, the temperature would have been this. Okay. So, this is another way of just quantifying the specific intensity, and it tells you the brightness of the radiation. This is called, it associates a temperature, which quite often is easier to interpret. We have a better feeling for it. Okay. So, it comes out in units of Kelvin. The specific intensity is in units of joules per meter square per hertz per second per steradian. This quantity is something easier to interpret. It comes out in the units of Kelvin, and it is a measure of the brightness of the radiation. Okay. It is called the brightness temperature, and it is extremely simple. The relation is extremely simple in the Rayleigh-Jeans limit. Otherwise, you have to put in the Planck formula and determine this. Okay. And it often gives you a good idea of what is going on in the in radio astronomy, where this is extensively used. Now, the radiative transfer equation in the Rayleigh-Jeans limit, the radiative transfer equation also takes on a very simple form. So, in the Rayleigh-Jeans limit, we can, instead of using specific intensity, we can just use the brightness temperature. So, the radiative transfer equation becomes d by d tau of the brightness temperature is equal to, the specific intensity is now replaced by brightness temperature. There are all these multiplicative factors which will appear throughout. This is equal to minus Tb plus the temperature of the source. The source function gets just replaced by the temperature of the material through which the radiation is passing. Okay. So, the radiative transfer equation itself becomes much simpler in the if you use the brightness temperature in the Rayleigh-Jeans limit. Okay. And what happens now? So, if the medium is optically thick, we know what happens. The specific intensity becomes equal to the source function, right. That is what we have seen. If the material is optically thick, whatever specific intensity, whatever brightness comes on it, what comes out is basically the source function, if the material is optically thick. So, here what happens, whatever be the temperature, brightness temperature of the incident radiation, the brightness temperature of the radiation that comes out is essentially the temperature of the material. It is a black body with that temperature, black body spectrum. Okay, it is the temperature of the material. Okay, so, this is one of the temperatures. It is called the brightness temperature. Then we have another one which is called the color temperature. Okay. Now, just before finishing this brightness temperature, see, the brightness temperature is used in for any arbitrary radiation. I just equate it to the Planck spectrum at that value and find the temperature. Okay. So, let us consider a hypothetical situation where I measure I nu from some source which looks like this. Okay. This is obviously not a black body spectrum. So, if I calculate the brightness temperature at this point, what will I do? I will find which black body spectrum goes through this, and I will associate that temperature. If I find the brightness temperature at this point, again I will find which black body spectrum, it will be a different one that goes through this, and I will associate that temperature. Okay. So, if I have something that is actually not a black body, then different parts of the spectrum will have different brightness temperature. I hope that is clear. If it is exactly a black body, I will get the same brightness temperature throughout. Okay. There is something called the color temperature. Let me now tell you what the color temperature is, okay, which again is quite useful sometimes. Sometimes I cannot measure the specific intensity. There are situations where I have no idea of what the specific intensity is. Okay. I can only measure the flux. Okay, there are situations. Let us consider this situation. Suppose I have a source over here and my telescope, the instrument that I am looking at, has an angular resolution which is larger than this. Okay. Now, what is the specific intensity? The specific intensity is the radiation coming per solid angle. I do not know the solid angle subtended by the source, because the source is smaller than the smallest angle I can measure. So, I can only measure the flux, the total radiation coming from this. To determine the specific intensity, I have to actually brightness, I have to divide by the solid angle subtended by the source. That will be some number, okay. But I cannot do this because I cannot determine this. It is smaller than the smallest angle I can measure with my telescope, which happens for example to stars. I cannot determine the diameter, angular diameter of stars. It is much smaller than the resolution, the smallest angle that can be measured by most telescopes. So, I can measure only the flux, which is the integral of the specific intensity, which is the specific intensity into the solid angle of the source. I do not know what this is, so it will remain there as an unknown. Let us assume that the specific intensity is roughly constant over the source. Okay, so I have a measurement of the flux F nu, and I find that its shape is very similar to a black body, but I do not know what the, I obviously cannot say it is equal to a black body because I do not know the scale. I cannot say that it is equal to this B nu because I do not know the scale, there is the solid angle involved. Okay. So, what I will do is I will just take the shape of the flux as a function of frequency and fit it to the, see which black body spectrum the shape best matches, okay, and then use that to determine a temperature called the color temperature. Okay. So, possibility is I could see that the flux has a peak, and we know that the position of the peak is unique for a black body, right, uniquely determined by the temperature. So, if I can measure where at what frequency the flux is maximum, I would then get an idea of the temperature, and that would be one estimate of the color temperature. Okay. So, this is what the color temperature is all about. We have a third kind of thing, which is a third kind of definition, effective temperature, which is also used, and this is called the effective temperature. So, suppose I have a source for which I can measure the total flux that is being emitted, okay, total flux that is being emitted. So, if I can measure the total flux that is being emitted by by the surface of, from that surface of the source integrated over all frequencies. Okay. So, this is the flux emitted per area of that source, okay, and we know that if it is a black body, this will be sigma T to the power 4. So, if I can measure the flux that comes from per unit area of that source, for example, the sun, I know the area of the sun, I know its radius, I know the, so I can determine the area, and if I know how much energy is being emitted per unit area of the sun, how much flux, so then I can equate it to sigma T to the power 4, and this is what is called the effective temperature. This again is correct, perfectly correct only for a black body, but in astrophysics we apply it, we have to associate, we would like to associate a temperature with with the radiation. So, if I apply it to some other source, then the temperature that we estimate using this is going to be called the effective temperature. So, if I tell you that the effective temperature of the sun has some value, basically we have estimated the flux that is emitted by unit area of the sun and just fitted it to this Stephen-Boltzmann law. put it in the Stefan-Boltzmann law. Now, the temperature of the surface of the sun may not be that, it will be that if the sun were exactly a black body, if not it will be something different, but we have been able to, we have used this to characterize the radiation from the surface of the sun. Okay. So, let me bring today's discussion to a close over here. Today we learned the nature of the Planck spectrum or the black body spectrum, how it is related to the Bose distribution, and from there we derived the Stefan-Boltzmann constants, and we then looked at various effective temperatures that are defined in, often used in astronomy and astrophysics.